And then he joined University of Michigan as a full professor, and he has a number of awards from Control System Society, IEEE, and AIAA. I'm just honored that he accepted our invitation to be our guest speaker today. So Ilya, it's yours. Take it now from here.
Thank you very much for the very kind introduction. First, I wanted to check that you can see my slides. Is it okay?
They are visible.
Yes.
Mm-hmm.
Okay.
Yeah.
All right. Great. So it's a great pleasure for me to give this talk and say a few words about some of my research, and that concerns model predictive control and computations. More broadly, I work in the area of control of systems with constraints, in particular safety constraints, and enforcing these constraints becoming more and more critical issue in systems that are being downsized or made more agile and have to operate more and more at performance limits. Effective controllers for such systems must be nonlinear and predictive, and nonlinear because what you do to avoid constraint violation can be very different from what you do to track nominal reference commands. And they have to be predictive because what you can do now can put you in danger of constraint violation later. It also helps to be predictive about disturbances and environment that surrounds you. The case when you have both state and control constraints, actuator limits, is perhaps the most difficult because these are situations where systems operating under such constraints, they must be smart. And then if you think about autonomous systems that operate in dynamically changing environment, they must be able to learn and adapt. I will not dwell on this. These are all familiar examples what bad things that can happen if one violates constraints, various type of rollovers that can occur, compressor surge, battery overheating, violation of loads during maneuvers or during gust encounters, and issues related to pilot-induced oscillations that also typically involve constraints, saturation limits on the actuator. So it's a pretty important problem to be able to deal with constraints and enforce constraints. Now, one of the key tools and common approaches for dealing with constraints has been model predictive control. And the idea of model predictive control, it's first of all, it's a feedback control, and is defined by the first element of the optimal control sequence obtained as a solution to a constrained discrete time optimal control problem. And typically you see something like this. So there is a cost function that you'd like to minimize, consisting of a terminal cost and then a running cost. I often use hats to denote predicted state and control values over the prediction horizon of, say, n steps. And then that's what you're trying to minimize, subject to your initial state in prediction being the current state of the system. Typically, we worry about reference tracking commands. And so we have this R, which is the reference. And then the constraints are enforced by virtue of imposing them in this optimization problem formulation. And so then the first move or the first element of the optimal control sequence obtained as a solution to this problem is assigned to a feedback law, and that's precisely what we mean by model predictive control law. So it becomes a function of the state and the reference. Often one thinks in terms of this type of a diagram, where we have a control sequence that we optimize over the prediction horizon. We predict the response, make sure it satisfies the constraints and minimizes the cost function, and then we repeat this process at the next time instant. Now, MPC has emerged in late 60s in academia and in late 70s in industry, fairly independently, I would say. And it has been a vibrant area for academic research for several decades. It's now at a stage where it has a strong theoretical and computational foundation, and its adoption by industry has been growing. Traditionally has been used in the petrochemical process industry, but there have been notable recent successes in aerospace and automotive industry, and this is not just the sort of laboratory experiments, but that's in production. Now, what I'd like to do for this talk is that I'd like to focus on a couple of topics relevant to model predictive control, in particular the interplay between computations and closed-loop properties. If you dealt with model predictive control computations, it's a significant challenge in some of the fast applications where you don't have as much time to compute. And so traditionally, we've been looking at addressing these problems by speeding up and increasing reliability of computations, basically working on solvers for model predictive control. And I'll give basically a snapshot of this work. More recently, we've looked at these issues of what does it mean to solve the optimization problem in model predictive control inexactly, what does it mean in terms of closed-loop properties and being able to satisfy constraints. I'll tell you a bit about this work. And then turns out that one can develop supervisory schemes, extra schemes that augment model predictive controllers to improve reliability as well as ability to find solutions in limited computation time. And this is the idea of this reference governors for model predictive control. I will probably not have time to talk about multidisciplinary design optimization. Turns out there is a intriguing and interesting connections between model predictive control and multidisciplinary design optimization. And just as a hint, turns out that in both cases, you have a bi-level optimization problem or parameter-dependent optimization problem. And so you could sort of take some of the ideas I'm going to talk about in model predictive control and apply them to multidisciplinary design optimization. I will probably not have time to speak about it, but if that's an area of interest, I'll be very happy to talk about it afterwards. Let me start with a few applications where we've been using model predictive control and where computational power and ability to compute solutions has been an issue. And so one is that if you think about small aerial platforms like quadcopters, for example, or some kind of blimps for warehouse servicing, you don't have a lot of computing power. And so implementing MPC in these applications represents a fairly significant challenge. This is an example where we are testing MPC controller for trajectory tracking. This is in our M-Air facility at the University of Michigan. We can test this during outdoors in including in bad weather. So this is a nice facility that we have. But MPC solutions based on onboard optimization we are able to realistically implement are limited due to, once again, lack of the computing power. Here's an even more significant challenge from both computational control perspective, and that involves control of aircraft with high aspect ratio flexible wings. Such aircraft are of great interest, of course, as high aspect ratio wings reduce air drag and fuel energy consumption. And you can also use them as high altitude, long endurance platforms. Unfortunately, these aircraft are also very flexible, and so they can experience high deflections and loads as they're exposed to maneuvers and wind gust disturbances. Furthermore, they have fairly complex dynamics, and typical physics-based models for them are high order, hundreds to thousands of states, and it's not straightforward to use them directly for control. There's also numerous structural and control effector constraints which need to be enforced during aircraft maneuvers or when responding to gas disturbances in order to preserve aircraft structural integrity. Another area for MPC applications we've been looking at is in the area of spacecraft control, and in particular, there is an increasing interest in operating beyond geostationary orbit in Earth-Moon space, XGEO setting, so to speak. And there is some interesting periodic, quasi-periodic, and chaotic orbits in that setting. The computation time, depending on an orbit, the computation time is not necessarily a major consideration on these orbits, but reliability of the computations and being able to find solutions is, because to enable low fuel consumption, for example, during station keeping, there needs to be, or they're beneficial to use special formulations of model predictive control, which use more accurate models with more accurate physics representation, as well as non-standard choice of cost functions, such as sum of norm cost functions. And this non-standard or less standard problems, let's just say, they need to be solved reliably to be able to obtain low fuel consumption in these settings. Another application for which we successfully exploited MPC involved the reduction in emissions of diesel engines. And diesels are used to power trucks, heavy-duty commercial vehicles, but also ships and even some airplanes. And the controller architecture that emerged was actually quite interesting and involved an air-pass controller. So there were feed-forward and feedback MPC controllers. And there was also a supervisory MPC controller that would manipulate the set points to this inner loop air-pass controller that would manipulate engine actuators. And so what's interesting that while this architecture is quite complex, it has enabled us to improve the transient control of the engine. These are experimental results, and we've done very extensive testing, also comparison with existing baseline controllers. And so by better control of the engine intra-engines, we're able to reduce oxides of nitrogen emissions without increasing beyond acceptable limits the smoke emissions as well as hydrocarbon emissions. And then with the help of some of the methods developed in our research, we have been able to maintain the worst case total computation time for all these three controllers under 1 millisecond in D-Space rapid prototyping system that was used for testing in this particular case. More recently, we have been exploiting neural networks for modeling emissions and developing special methods for the use of MPC based on neural networks for engine applications. And then as a kind of my final application that I wanted to briefly mention, MPC is increasingly being integrated into settings and applications that involve interactions with human agents. And significant challenge in such applications is how to predict the response of human agents and how to non-conservatively operate in such environments. In particular, in a highway emerging vehicle has to nudge its way through interactions with other vehicles. And if there is a dense traffic, that's a non-trivial thing to do if the vehicle is automated. So in our work, we have been exploiting game-theoretic multiple model framework to represent human-driven vehicles, and then Bayesian inference to assign the probability of to each model of each of the surrounding vehicles, as well as stochastic model predictive control to ensure safety over all high probability interaction scenarios while minimizing average cost. Currently, we are limited to 4-second prediction horizon due to, once again, large computational effort in handling multiple scenarios in model predictive control. So motivated by this and other applications, we have been working on various approaches to address the computational challenges in model predictive control, and we approach this really from several different directions. Traditionally, we have been trying to develop and improve computational solvers, computational optimizers for online optimization, and several related contributions. This is work with multiple collaborators who are co-authors on joint publications. They are summarized here. I'll give you a flavor of one of these developments on the Newton-Kantorovich method, but we've done quite a bit of work on sensitivity-based methods, predictor corrector methods to speed up the computations, semi-smooth optimization solvers for QP. We've developed a number of solvers that can be downloaded from GitHub, such as FBRS and FBStab. various constraint aggregation techniques, and approaching problems also from perspective of symbolic computations and symbolically optimizing the implementation of the solver that turns out to also reduce the computation time, and various other ideas. So I'll speak about just one approach here, which we call inexact Newton-Kantorovich method for model predictive control. And I want to go to describe it, I want to go all the way to very classical idea of Newton's method for solving a smooth equation, smooth nonlinear equation of f(x) is equal to 0. So what you typically do is that you take a guess for the solution, x0, and then you see where the graph of the function is. You linearize this graph, so you obtain a linear equation, then you solve this linear equation, you find the next guess for the solution, x1, and you repeat this process, and if everything is known exactly, you converge quadratically to the root of the function. Now, it turns out that there is a Newton-Kantorovich version of the Newton's method where you don't recompute the slope, so you don't linearize your equation, and you just continue to iterate with the slope that has been computed at the initial point, or it could be some other slope satisfying certain conditions. And as you can see, you converge slower, but you still converge to the root. And in fact, there is an inexact version of Newton-Kantorovich method where you don't even have to solve the system of linear equations or the linearized equation here to completion. You only need to solve it up to certain tolerance, which should be increasing as you approach the root. But with this inexact version, you still are converging to that root. Now, in a setting of model predictive control, these ideas of inexact Newton-Kantorovich method are very appealing because often you have a pretty good idea of the solution if you use worm starting from the previous time step. So you computed the solution, you can worm start your optimizer, and you're typically pretty close to the solution. So having some cheap iterations, fairly cheap iterations, to sufficiently improve on that solution is often enough in applications to model predictive control. And so what happens is that that's an idea that can help. Now, when you deal with model predictive control, the setting is a little bit different because it's a constrained optimization problem. So you deal with Karush-Kuntaka conditions. They can be restated as in the form of variational inequalities. These are just KKT conditions. They are a little bit more complex objects to work with than smooth nonlinear equations, but it's possible to extend this inexact Newton-Kantorovich method to the variational inequalities. We've done it in one of our papers in transactions on automatic control. And it's possible to get guaranteed convergence rates as well as the estimates of region of attraction. And then you can couple these ideas with a variety of methods for solving MPC problems. For example, sequential quadratic programming. You could integrate these ideas in a quite straightforward way to solve the necessary conditions for optimality. And indeed, you obtain, in examples, for example, to spacecraft attitude control, you can demonstrate reductions in both average runtime as well as the maximum runtime per iterations for solving a model predictive control problem by taking advantage of this inexact Newton-Kantorovich ideas. Now, this is a brief flavor of the work that we have done in the past, and more recently, we started to look at what happens with model predictive control when you rely on inexact optimization. So suppose you cannot solve the problem in MPC exactly. What happens? How is the closed loop performance is affected? And so the optimization algorithm in model predictive control, which is running with fixed number of iterations. So we are assuming there is some kind of iterative solver by which we solve the optimization problem. We are only able to perform a fixed number of iterations that our processor allows. And then we are also using a worm starting from previous time step. And so the key realization is that this becomes a dynamic feedback law. So ideal optimal MPC, here I don't have a reference command, I just have state and control. So if you think about ideal or optimal MPC, you take a state, you solve the optimization problem, and that produces the control signal U. And so this is a static feedback in such a setting. Now, if you do suboptimal MPC so that you solve this problem inexactly, relying on fixed number of solve iterations per time step and warm starting, then the picture changes and your controller becomes dynamic. So your optimizer acts as a dynamic controller. It has an internal state, Z sub k, and this is just a guess for the solution that you improve by running L iterations of the solver per time step. So the optimizer starts running in parallel to the plant. And then the question is what happens to properties of this closed loop system. In simulations, you could clearly see that there is a strong dependence on the number of iterations that you're able to perform. For example, with the optimal solution for MPC solving this problem to completion, you can balance the inverted pendulum on a cart. And you can do it if you allow sufficiently large number of iterations. But if the number of iterations is sufficiently small, for example, 5 in this case, the stability, you don't have closed loop stability here, so the stability is lost. And of course, this type of considerations become practically important when you have to, for example, land a SpaceX rocket, which has somewhat similar dynamics in this type of situations. So we've been looking at bringing various tools from control theory into analyzing this picture and obtaining conditions on how many iterations we may need to obtain, for example, closed loop stability, to obtain ability to be able to satisfy the constraints. And so one of the useful tools is a small gain theorem. And the key idea here is to think about this closed loop system where we rely on inexactly solved MPC problem as an interconnection of two systems. One is the ideal closed loop, which is based on ideal optimal MPC, and then optimize the error subsystem, which creates pretty much an input disturbance. So the ideal control action is being modified by this computational error. And then this optimize the error subsystem, the disturbance of the input to it's a change of the state in a plant. Because if the plant state doesn't change, we're solving the same optimization problem. So this delta X is the input. And the key realization is that for a variety of optimization algorithms, if you think about input-output gain from this input to this output, then that gain can be made arbitrarily small by increasing the number of iterations. And so what this means is that you could show that there exist a number of iterations, L star, that if you perform more iterations than this L star, then the closed loop system is going to be asymptotically stable at the origin. And in fact, it's going to be locally input to state stable. And this line of reasoning also yields procedures to estimate L star for certain problems, in particular for case of linear systems and quadratic cost, as well as constrained region of attraction. And we have been actually exploiting this type of estimates in practical problems, for example, stabilization of drifting vehicle dynamics. This is open loop unstable equilibrium that you might use, for example, during car racing. And the current estimates, the analytical estimates, they tend to be conservative. Empirical estimates, if you just run closed loop simulations, they tend to be require less iterations. But the fact that you have this analytical estimates for the number of iterations is interesting. First of all, it is an analytical guarantee. But secondly, you could study how you should reformulate your problem in such a way as to reduce this L star. For instance, you could almost guess that the horizon of your problem, if you increase the prediction horizon of the MPC problem, that would typically result in increase of L star, and that is indeed the case. But let's say you are in a situation where L star is unacceptably large. How can you reformulate your problem to decrease L star? Well, if you don't want to change the horizon, one other thing that you can do is, for example, increase the control weighting. So if you think about typical linear quadratic cost in your optimal control problem, you can increase the R matrix or entries in the R matrix, and making control more expensive decreases L star. So you can address this type of situations. Now, let me briefly talk about another idea which can enable operation with very small number of iterations per time step, even if MPC optimization problem is solved to completion. And we refer to this idea as the computational governor. Now, recall again that in model predictive control, the discrete time optimal control problem is solved numerically using a numerical optimizer. And this is typically done with the worm starting from a previous time instant. Now, if the system is close to steady state, you are at a set point, the worm started MPC solution is not so different from the optimal solution. And typically, one iteration per time step is sufficient for convergence. The spike in the number of iterations that the optimizer needs to perform occurs when there is a large change in the MPC problem data. For example, there is a step-like change in a reference command. So R here is a reference command to which the output responds. And if you look at the number of iterations that you need to perform, that's typically where you see the spike, when the problem data changes very, very abruptly. So then the idea is pretty clear. What one can do is replace the step change by perhaps smaller step and a ramp. And if you do it carefully, you could compute the solution reliably with perhaps just one iteration of the solver per time step. And of course, the question is how to construct such a computational governor that would make such a replacement of the original command R by altered command, which we're going to denote by V, without leading to too much performance degradation. And from the analysis perspective, the problem is not straightforward because multiple variables are changing simultaneously. The state of the system, the solution evolved by model predictive controller, as well as this V. Now, before I talk about computational governor, let me first mention that the computational governor is a variant of the so-called reference governor. The reference governor, it's a safety supervisor for reference commands sent to the system. So traditionally, reference governors have been developed for enforcing physical constraints in the system, for example, limits that physically exist. So the computational governor, it's a variant of the reference governor that's applied to computational constraints or cyber constraints, if you like. So the idea of the reference governor is that it's a scheme that's augmented to the nominal controller. It monitors reference commands that may be issued by an operator or high level in autonomous control system, for example, higher level controller. If these commands are determined to be unsafe, it's going to modify them, and it's going to try to to keep this modification to a minimum. And typically, you solve some kind of optimization problem where the output of reference governor is as close to the input, subject to safety condition on the modified state and command pair. And then turns out that such schemes can be built that are fairly easy to implement, as well as they have a property of fast online computations with especially suboptimal solutions. For example, this is something we call scalar reference governor, where the output is just a linear interpolation of previous output and current reference command. And this is a cartoon, but perhaps it's a conceptual way of thinking about reference governors. So here we have a user that issues a command. The command is not safe. There is a nominal controller with a PID tattoo here. And then the reference governor modifies this command to sort of go around the iceberg and avoid violation of constraints. If you like to read a little bit more about reference governors, there is a survey paper in Automatica that we published a few years ago, and there have been multiple extensions of the schemes, as well as applications in many domains. In my group, we worked quite a bit on applications of reference governors to engine control, propulsion systems, and including experiments in vehicles. And this is an application done a few years ago where we've deployed such reference governors to prevent the surge of the compressors of the engine. And this is where you try to maintain the trajectory on the compressor map, compressor flow versus compressor pressure ratio outside of the surge region. And you can enter the surge region if you allow a very rapid reduction in compressor flow. So the idea is to slow down this reduction, so you tend to stay in this green region. And that's an example where we've done extensive vehicle experiments and implementation of such schemes. Finally, I'd like to, just as an aside on the reference governors, I'll come back to computational governors, but as an aside, I wanted to mention our recent work with Naira as well as with Penzao on integrating reference governors and L1 adaptive control. And this is a recent paper in Transactions on Domestic Control that we had. The idea is that L1 adaptive control would match the uncertain closed loop dynamics to a normal model. And the approach is nice because both state and control constraints are considered and enforced. Many approaches for handling constraints under uncertainty exist in the case of just state constraints, and assuming that you have basically any control authority you like, the problem is much tougher when you, in addition, have control constraints, and this is the case handled in the paper. And one of the things we've shown is that there is a reduced conservatism by taking advantage of adaptation versus a robust reference governor that tries to protect against worst case uncertainty without making any attempt to estimate and compensate for it. Okay, with that aside, I want to come back to computational governor, which is a variant of reference governor scheme, but it's used to enforce computational constraints. So how do we construct that? And here I'm going to give a few more technical details, perhaps. I'll sketch them so that if you're interested in details, you see what it involves. So first, we are looking at linear quadratic MPC problems. So our cost is quadratic and the model is linear. And it is well known that in such cases, we have a quadratic programming problem. And if we condense, so our optimization variable is a control sequence. So we stack control moves on top of each other. And with respect to this control sequence, we end up with a problem which is a quadratic programming problem, minimizing quadratic function subject to linear constraints. It's a parameter-dependent problem because it depends on the current state as well as this modified reference command that we have. And so how do you solve a QP? Well, you apply Karush-Kuntaka conditions. And this is pretty much stationarity, a condition, primal dual feasibility, and complementary slackness, where here we introduce this homotopy parameter eta instead of equating this to 0. And this is a typical approach in interior point methods. So then what we do, so lambda here are the Lagrange multipliers as a slack variables. They have to be non-negative, and we employ logarithmic transformation. So the Lagrange multipliers are parameterized in terms of this new variable gamma. And note that this is always non-negative, S is always non-negative. And if you take lambda times S, you get precisely eta. So the this complementary slackness condition is satisfied thanks to this logarithmic transformation. And now what's very interesting is that instead of system of equations and inequalities, you just have a system of nonlinear equations. And that's something that you can solve using Newton's method, right? You could, once you make these substitutions, you obtain just a system of equations. So this is a Newton step. So D is a Newton step. This is what you get from linearizing this nonlinear system of equations and figuring out the solution of the linearized system. So this is D, and pretty much this is what you do to adjust this log space variable gamma. Now, what I just described here is something called logarithmic domain interior point method, which is a nice way of solving QP problems, and that's what we apply our computational governor to. So the structure of computational governor is similar to scalar reference governor. So the V sub k, the modified reference, is the previous reference plus kappa, and kappa is between 0 and 1, and this multiplies the difference between a true reference command and previous reference command. So pretty much it's a linear interpolation function where kappa is an adjustable variable. And it turns out that to determine by how much to adjust your command, you have to solve a linear program, and you solve this linear program simultaneously for two variables. One of them is this kappa, and the other one is the homotopy parameter eta that I've introduced. And turns out that the key constraint in this problem is that the D is the Newton step. It has to be less than 1 in infinity norm. So this is the key condition, and I'll explain what this constraint involves. Other conditions are the kappa has to be between 0 and 1, and then eta for homotopy parameter, we typically pick some kind of a range. Ideally, homotopy parameter has to be reduced to 0. Now, what is gamma tilde? Gamma tilde is a warm started value of the log space variable, and pretty much we use a procedure grounded in classical MPC, shift by 1 and pad by 0 to figure out this initialization. So the condition that maintained by computational governor, this is our computational constraint that keeps our solver happy, is this D, which we can explicitly compute, this Newton step, has to be in infinity norm less than equal than 1, and when it's evaluated at warm started log space variable. So this is the condition that effectively tries to bound the suboptimality of warm start. So we are trying to make sure that when we warm start our solver, our warm start is not too, it's not too suboptimal.
Where do you go?
Sorry, is there a question online?
Okay.
No, I think Louis is just not muted. Louis, please mute yourself. It's Louis' conversation.
Oh, okay. So there is no question. So I can continue. So why is this condition? So this is the constraint that we derived in the analysis of this problem. And it turns out that if you satisfy this constraint, then all the iterates of this LDIPM algorithms, they tend to be in a guaranteed fast convergence region, which means that we only need very few iterations to converge to the solution. They also guaranteed to be all iterations, if this condition holds, all iterations are guaranteed to be primal dual feasible. And that's actually quite a nice feature, because this means that feasibility is going to be maintained with respect to state and terminal constraints, even for short horizon MPC. So I could use this actually enables the use of short horizon MPC. And then the state and control constraints would be again strictly enforced. Now, we have a paper that also does more analysis of the closed loop properties with such a computational governor device, and we can guarantee standard reference governor properties. That is, the modified reference command converges to true reference command in finite time. This happens for constant and strictly steady-state admissible references, and of course the states converge asymptotically. And in practical applications, we see at least an order of magnitude reduction in the computational time that we need. For example, this is for vehicle lateral dynamics problem. And also this gives us a very nice ability to use model predictive control with short horizon while being able to enforce extra, while being able to strictly enforce state and control constraints. So here's an example where you're enforcing extra constraints of a short horizon solution, and number of iterations of the solver is equal to 1. I'll skip that slide. Some experiments, first of all, in a laboratory environment. So here we are balancing inverted pendulum on a cart. And you could see here that what happens, we are commanding different position to our cart, and the computational governor modifies the step change in the position. We are able to, we only need one iteration of DIPM solver to control this system. And so it's a fairly low computational effort that achieves through this command filtering action. And then these solutions that they actually made a practical impact. There was an implementation done by Toyota, and this resulted from our joint project on these topics with them. The solution that they have implemented is strongly motivated by what I have presented, but somewhat perhaps different in details. But nevertheless, that's this computational governor is now in production. And we have been continuing the work on computational governors. The solution that I presented is specific to a particular solver, LDIPM. And so the question is that you could perhaps develop such solutions for other solvers used in model predictive control. In fact, initially the thought is, well, we can generate a very large sequence of papers just modifying this idea for different solvers. But it turns out that the details are more involved, and we've tried to develop such a solution for alternating direction method of multipliers. It's a popular first-order method, and we will have a paper at the upcoming American Control Conference that reports the details. But turns out the details of the solutions, the motivation is the same and the intuition is the same, but the details are quite different. And one difference is that the early termination of ADMM may give an infeasible solution, typically gives you an infeasible solution. So that requires that if you rely on inexact solutions, you also have to tighten the constraints. And that changes quite a bit the computational governance strategy for reference command modification. But looks like we've been able to develop it, and you're able to show finite time convergence and feasibility, give feasibility guarantees with respect to original constraints, but again, quite a few details. So it seems that if you pick a different approach or different optimization algorithms, the way you couple the computational governor to it may be different, similar in spirit, but quite different in details. How much time do I have left in the talk?
You have still maybe 5-10 minutes to talk. I mean, I'm sure there will be questions. And
okay. So let me continue a little bit on this line of the talk where so I talk about computational governor, and this work made us realize that you could develop a number of supervisory schemes to augment MPC controllers to enable some beneficial properties. For example, reduce computational time, perhaps increase the reliabilities of the solution, and so on and so forth. So one other device that we've recently, or one other scheme that we recently constructed, is something that we call stability governor for receding horizon MPC. And the challenge that this addresses, it's a practical challenge. So if you think about assuring asymptotic closed-loop stability under MPC feedback, this is typically guaranteed through the choice of the terminal penalty and terminal set constraints. So if you look at the problem formulation that you solve in model predictive control, you would have something like this. And at the end of the horizon, your terminal set, this xn hat, you would require that that belongs to a terminal set, and it has to be a safe invariant set where you have a certain decay properties for your terminal penalty function. And then you also use the terminal penalty as a part of the formulation of your MPC cost. And that's one of the approaches, classical approaches to ensure closed loop stability in model predictive control. Now, in practice, often you try to avoid imposing these terminal constraints, and there are various reasons for why this is the case. One is that the terminal constraint complicates online optimization. For example, this constraint may be ellipsoidal, quadratic, even if your problem is for a linear system with quadratic cost. So it's quite a different constraint. It can be difficult to compute offline for practical systems. But more importantly, its use can degrade closed loop performance because a lot of the energy or a lot of effort of the controller goes into satisfying this terminal constraint rather than trying to minimize the cost function that you truly care about. And so in practice, the practitioners, they often avoid actually adding this constraint, but then what happens is that the associated closed loop stability guarantees are lost, and actually the properties are lost as well because of the reduction of the region of attraction when you get rid of this terminal constraint that occurs in many problems. So we wanted to address this situation with adding a supervisory unit, which we call stability governor. And I'll show a few details here. So we are going to drop this terminal constraint. We are going to look at terminally unconstrained MPC problem, where we take our reference command R and we replace it by V, and V is going to be output of this stability governor. We are going to look at a linear quadratic MPC case. So it's a standard linear quadratic cost, quadratic terminal penalty function as well. And it turns out, in interest of time, I'll skip some details, that even if you drop this terminal constraint, there is still a guaranteed region of attraction of this terminally unconstrained MPC. And this is a sub-level set of the optimal cost to go of this Vn alpha. And the size of that sub-level set depends on a couple of parameters. One is the horizon of the problem n. So the longer the horizon, the larger is the region of attraction. But it also depends on the terminal penalty, this lambda, as well as the size of the so-called implicit terminal set, which is a safe sub-level set of the terminal penalty function. So bottom line, turns out there is some region of attraction that you can prove that exists for this terminally unconstrained case. But the trouble is that it's typically much smaller than the region of attraction that results from a terminally constrained MPC law. And so what we then do is that we add this stability governor as a way of enlarging the region of attraction. And so the logic for the modification of the reference command is exactly the same as it was before. The procedure to pick this kappa parameter, it's a bit different. But the key idea is that we always maintain the state of our system in the region of attraction, guaranteed region of attraction for the modified reference. And so as a result, with this trick, we are able to maintain stability for shorter horizons and smaller terminal penalty. And really, the whole intuitive idea is that the region of attraction that we get thanks to modifying this reference is the union of all these regions of attractions that correspond to individual values of the reference command. So we get much larger region of attraction by doing this. I'm going to skip the details, but just mention that the procedure for selecting this kappa is explicit. You could actually compute this in a very simple way. And then we had a paper in, I believe that was in Automatica, where we show recursive feasibility, asymptotic stability, and finite time convergence properties. So there is analytical guarantees for such a scheme. Just to briefly show the results here from one of the simulations, which also bring an important point across. So here I have an ungoverned case, horizon of 85 steps. This is for the inverted pendulum on a cart. And I'm giving a command which is shown by this red dot. And this is a very large change in the command, or large command. And so my initial state is outside of the region of attraction of this red dot. So my closed loop is unstable. Now, if I use the same horizon, but then I apply my stability governor, you could see that my red dot is not commanded to the system immediately, but it's sort of slowly, well, as fast as possible, subject to conditions I described, driven towards the blue dot. And now the state always stays in the region of attraction, and so we are able to maintain stability here, as well as to, of course, satisfy constraints. And in fact, I could reduce the horizon of my MPC problem, and that has the benefit of decreasing the computational cost. Now, the price to pay is that my motion is less agile, it's more slow, but I'm still maintaining the stability and still reaching my point while satisfying constraints. Okay, so there is a variety of other things that you can do. We looked at problems that that involve model predictive control that accounts for preview information. For example, in some problems, you might have preview of loads, perhaps road terrain and vehicles, gust profile, perhaps with a LiDAR in certain applications. And so it turns out you can develop feasibility governor to help maintain feasibility for MPC with disturbance preview. And the details are in a paper that we recently had in Systems and Control Letters. I'm not going to have time to talk about multi-system design optimization. I'll skip that part, and I'll just go directly to my conclusion. So some closing thoughts for my talk. So in exactness of computations in MPC, that's obviously a practical issue because typically you encounter the need to, or the fact that your processor is not able to perform computations in practical applications, and clearly that inexactness affects closed loop dynamics and closed loop properties. So what's interesting is that you can analyze that and develop some analysis results and some guarantees. For example, you could develop bounds on the number of iterations to ensure closed loop stability for model predictive control, receding horizon MPC. I haven't talked about this, but we also looked at a shrinking horizon MPC, where the horizon doesn't advance into the future, but shrinks by one step with every step. So, for example, when I'm trying to give a talk, my terminal time of ending the talk is usually fixed. So I have to adjust to this end deadline. And so this is what we call shrinking horizon MPC. And turns out that you can also do analysis of inexactness in that setting as well. Now, the other key point is that you can develop reference governor-like supervisory schemes for MPC, and historically, reference governors were viewed as competitors to model predictive control because both schemes enforce constraints. But what we've been able to show that there is a nice synergistic way to combine them to be able to improve reliability of MPC, in particular with short horizon, reduce computational time, and expand the closed loop region of attraction. And finally, I haven't spoken about multi-system design optimization. If that's an area that you're interested in, please drop me a note, or I'll be happy to stay afterwards and speak a bit. But it turns out that in multi-system design optimization, the optimization problem itself has very similar structure to what you have in MPC, because you have parameters, design parameters that the optimization problem depends on. In MPC, you have optimization problem depending on the state of the system. So taking advantage of this analogy, you can take advantage of certain control theoretic tools such as small gain theorem to prove convergence, for example, of bi-level optimization algorithms. And we've done some initial work along these directions. And so I'll stop here.
Okay, thanks a lot. Let's see if we have questions from the audience. I'm sure there are a few. Who is going ahead with the question first?
Yeah, I can have a question.
Okay.
Well, so yeah, that was a very nice talk on all these MPC developments. And I just wanted to ask you one thing, for example, would be in the general MPC literature, is it always that the state is available, or if you have noise there, are there any sensitivities to all of that? How does it affect in the measurement of the state? And the other thing is, actually, I found very interesting to all this governor development, and because in practice, what are you going to have? You're going to have a bunch of governors together, or you're going to have a single system? What determines what kind of governors you're going to put there? So that was my...
Yeah, thank you very much. These are very nice questions. So, of course, in practical applications, having access to states, that's a major issue, right? Because you measure outputs, and then how do you determine the states? And so there is certainly a body of work on output feedback model predictive control. In practical sense, what people are trying to do is to develop a state estimator or an observer. I should point out that in a recent work with Dennis Bernstein, where we looked at something called predictive cost adaptive control. It's a variant of adaptive MPC. We've actually tried to stay away from state-based models with unmeasured states and base the models entirely on input-output framework. So the states are delayed outputs pretty much. And so that has an advantage that you don't need an observer except for perhaps noise filtering or something like that. And so I think what you suggested is that there's definitely a need to consider state estimation and state estimation issues in implementation of a model predictive control. There is work in the literature, and I know that you know that such developments exist. In all the work that I have presented, the assumption has been that you have exact state measurement. So there's plenty of room for further work to look at more interesting cases where, for example, you don't have exact state measurements. Now, the other question is also very nice in the sense that what governors do you use? It's one of the cases where we've done work on several schemes with somewhat different motivations. And perhaps at the moment, we don't see forest behind the trees yet, because I think there is probably an opportunity to unify some of the schemes. At the moment, the schemes that we are developing are tailored to specific situations. For example, even computational governor that I showed, it's tailored to specific optimization solver, LDIPM, and takes advantage of certain estimates that exist for that solver. Now we can abstract out and say if these estimates hold for another solver, then we can still apply the same construction. But I would say that we, at least in our group yet, we haven't been able to complete the story. I think it's an area that certainly more work can be done. This mechanism of using reference governor to expand the region of attraction, that's common to all governors, and I think it kind of naturally emerges for whatever solution we sort of look at. But ability to satisfy constraints, in particular computational constraints, that so far is specific to perhaps solvers and also aspects of the problem. Yeah, so we'd like to find a way of unifying these developments for sure. I was obviously joking when I said that, well, there's hundreds of solvers and you could kind of have factory of papers, right, developing these devices. I mean, we don't want to do that for sure. We would like to find unifying solution. But right now, the solutions we have are specific to those situations that we've considered.
Yeah, you may have a bunch of these governors and then switching over them, but then you'll have to have a switching governor.
Right.
So.
And the other thing that I was going to say is that when we are developing a governor, one important consideration is that computations for it have to be simple, because if the computations for it involve a harder problem than just increasing MPC horizon, you don't get anything back. So somehow the optimization problem in the governor has to be very, very simple to be able for the overall scheme to show advantages. And that's another important constraint, I think.
Yeah, thank you very much. Yeah, very interesting.
Thank you.
Next question.
Hi, Dr. Kolmanovsky. Thank you very much for your talk. I don't know if you can hear me.
Yes, I can.
Yeah, I have a question regarding what is your opinion about the role of simulations and sampling methods in the context of MPC. I mean, we have seen obviously simulations and Monte Carlo methods being vastly used for solving the estimation problem. Do you see any benefits in incorporating simulations like sampling, drawing samples to solve a difficult problem, and perhaps parallel computation and parallel computing, again in the context of MPC?
Absolutely, I think so. The large domain of model predictive control is model predictive control under uncertainty, and you have to sort of look at different ways of characterizing uncertainty. And there's stochastic MPC, there's robust MPC, and in particular, one of powerful approaches in stochastic MPC is scenario-based MPC, where you optimize with respect to a number of scenarios. And this sort of corresponds to sampling the uncertainty in a way. And so absolutely, I think that predicting what's going to happen in an uncertain situation, not with a single trajectory, but with a tube of trajectories, being able to do this in a computationally efficient way, also trying to take advantage of the fact that, well, when you advance one step, things didn't completely drastically change from previous time steps, so you could perhaps distribute some of the simulations over time. I think that this all represents a very nice area for research. I mean, the work, certain scenario-based MPC, the work has been done for multiple years, but I would say that there's still room for much further research, primarily because you need computation efficient way to predict the effects of uncertainty. If I may just mention another possibility that we've recently have investigated. This is to use the simulations, because you talked about using simulations, and this is to use the simulations for runtime assurance. So the idea is that you might have a hierarchy of models. Let's just say, for now, just two: low fidelity model and high fidelity model. And you want to do trajectory optimization based on a low fidelity model. But once you get this trajectory, you want to validate it, or not validate, verify it in simulations over the high fidelity model. And the simulations can be run fast. Optimization, it's more complex. For optimization, you may need to use low fidelity model, but for verification, just if you have a single trajectory to verify it, you can use high fidelity model. And so we've been trying to think a little bit about the setting where you have this low fidelity model for optimization and high fidelity model for verification. And it turns out that it's possible to introduce a reference governor in that setting. And what the reference governor does, it checks whether high fidelity model simulation satisfies constraints, and if it does, it updates the reference. If not, it keeps the old reference supplemented by some kind of backup controller. And so turns out that you can also develop a few results in that setting. I don't think this is all-encompassing result. But it's a development I think was relevant to trying to use simulations in online setting.
Yeah, thank you. So, to your knowledge, do you think that currently we're having the tools to connect something that's empirical, which is sampling, with something that's analytical, which is Lyapunov?
So there are results in that direction. For example, if you ask the basic question, can you construct, say, a Lyapunov function through simulations? So by there are certain results in the literature that enable to do that. But I think if you think about practical problems that if I give you a black box system, like often you have in industry, for example, we had projects where, for proprietary reasons, we would be just given a simulation model, and the question that we would be asked, let's say, can this black box exhibit a trajectory that satisfies certain constraints? That's a very different question, I think. And you don't even know the states. You don't know, I mean, this box can be hybrid. There may be some switching behavior inside. And so the answer that I would like to give is that, people, I think, thinking about these issues, of course, but there's significant room for further research and advances in that area. Because I mean, we had a project where, for example, we've been asked, well, here we have a kind of a high fidelity model of the system, and we know that the system doesn't. It doesn't appear that the system will be able to meet the requirement. Can you show that sort of by absolutely optimizing trajectories of that system as much as you can? And I'm not entirely even sure why we couldn't do this analysis on a low fidelity model, but I think our customers and colleagues that we've been working with were very interested in doing this on a model they have trust in. And they wouldn't be able to tell us what's inside. And even if they could, I'm not sure we would be able to take advantage of that because, again, of just complexity of that model. And it's, there are pieces of the code written in C as a part of that model. It doesn't have a kind of a state space form. You can develop low fidelity models based on physics that have state space form, but then you have to somehow match them to this high fidelity model, for example.
Thank you so much.
I'm not sure I'm answering your question.
No. I mean, in both of the cases, it was spot on. Thank you.
More questions?
Hi, Ilya. I have one question about the inexact computation MPC. So probably you already mentioned, but I wanted to double check. For the inexact MPC, can you adopt existing solver, for example, IPOPT, or you have to use some special solver?
I think it depends because, and it depends sort of in a practical sense, right? You can most of the solvers you can terminate early, right? So the question is really, can you use a solution that results from that solver? Right, that's the question. So, for example, I mean, even let's look at a basic example. In MATLAB, you can run fmin_con and you can set the number of iterations, right? So the question is then what happens to that inexactly determined solution? And so if this solution, and again, such thing as exact solution doesn't exist, right? It's typically some tight termination criterion which is being satisfied. And in fact, problems that we looked at for analysis, at least, not for everything, but for much of analysis, this tends to be convex problems. And if the problem is non-convex, even exact solution, right, may quote unquote may not be unique, and so on and so forth. So the issues are complex. But the key question is that if you rely on this inexact solution, what happens to your system? Are you stable? For example, in closed loop, are you able to satisfy constraints, right? if you're not able to satisfy constraints, can you tighten your original constraints so you satisfy tighter constraints that guarantees that despite inexactness, you can still satisfy the original constraints. And then, for stability, it's a more how many, under what conditions can you stop to ensure stability? And you can give various answers to that question, and and it all depends on sort of what type of conditions and what type of guarantees that you like to have. For example, we try to give conditions on a number of iterations because we felt that would be most directly linked to being able to assess what is the processor power that you have, right? And but you could pose the question in a number of different ways, and you could probably have different sets of answers. I'm not sure if I answer your question, but I guess your question was, can I just run a solver and stop it early? I think yes, absolutely. I mean, I think that you could stop the solver after one iteration, and in some problems that would be enough.
I see. Yeah.
Provided you use warm starting. I think that you might want to use warm starting. That is, you use solution from a previous time step to initialize the solution at the current time step. So essentially what happens is that you iterate over time, right? So this is time distributed optimization, where iterations of the optimizer are distributed over real time. You don't perform them at once, but you kind of spread them out. That's basically the picture. By the way, I should point out that there are formulations of MPC problems for which warm starting is not necessarily doesn't necessarily provide the best results, but that's a separate line of discussion.
I see. Thanks a lot for the clarification.
Thank you very much. Yeah.
Sheng, you have a question? You came up.
Yes, I do have a question. Thank you, Nera, and thank you, Dr. Kolmanovsky. Very exciting talk. My question is regarding the reference governor when you use it with an MPC. So that cartoon of sailing through an iceberg, that's a very interesting illustration of what I guess reference governor would do. So my question would be this, because normally we use MPC because there are constraints we want the system to follow. Like in that iceberg case, maybe you want the boat to go around to avoid collide into the iceberg. But in the same time, I think reference governor also can alter, say, the reference trajectory of the boat to avoid that iceberg. So I had this question of, if the constraint, we're going to place it for the system, where do we place it? Shall we place it in the reference governor for the reference, or do we do it with MPC for the control for the actual state, or a combinatorial way of both? So philosophically, if you can share your thoughts, that would be awesome.
This is an excellent question that I'm wondering myself about, because I do think that distributing constraints over various devices makes sense. And I can tell you, for example, that if you just use MPC with control constraints, you can have very fast solutions to the problems. If there are no state constraints, just control constraints, there is a variety of very fast solvers. And so you could sort of try to say that, well, maybe you could allocate all the state constraints to reference governor to handle, and then the MPC could handle just the control constraints. Now, you have to be a little bit careful there, because characterizing the safe set for an MPC controller or MPC closed loop system, it's non-trivial matter. And in prediction, you want to avoid solving MPC problems. So if the reference governor is based on prediction over forward time, you certainly want to avoid having to solve MPC problem, in a loop MPC problem, over each time step in the prediction horizon. It turns out that can be done, and we call this strategy incremental reference governor. And I'd be very happy to send you a paper on doing precisely that, or at least what we've done. I think maybe better solutions can be developed, but the one solution along these lines that we developed, I can send you the paper where MPC just handles the control constraints, And then reference governor handles all the state constraints in the problem. More generally, it's an excellent question that, I suspect the answer is ultimately application dependent. And you can ask this question in a variety of settings. But for example, again, if you have some constraints that are not linear, right? So let's just say you have a constraint which is quadratic or even some more complex nonlinear function. Well, if you rely on linear quadratic MPC solver, you don't have a direct way of handling this constraint. Maybe you can use polyhedral approximations or something like this, but you want to avoid it. So why don't allocate this nonlinear constraint to reference governor to handle, and then the rest will be done by MPC. And you have to do it carefully because computing the safe set for MPC controller or closed loop system with nominal MPC controller, again, may not be a trivial matter. And furthermore, if you do prediction-based reference governor, you want to avoid solving optimization problem at each time step of a prediction horizon, because then the complexity will be probably higher than what you get with nonlinear MPC. But there is a way to avoid it, which is simply use nice feature of MPC is that it predicts trajectory over the horizon in open loop. So just use that trajectory and modify it by backup control at the end of the horizon. That's basically the idea, and that's what you use in prediction. And it turns out you can build infrastructure on that idea. If you're interested, I can send you sort of a paper that has some of our results in that direction. But it's an excellent question. I don't know the ultimate answer, but I'm trying to think about it. And if you have some ideas, also feel free to. We can talk about it more. I'd be very happy to talk about it more.
Yep. Thank you for your answer and sharing your thoughts. I will follow up with you by email,
please,
so that I can read the papers you referred to. Yeah. Thank you.
Yes, please. Thank you.
More questions, although I think we have gone well over time. So if NASA people have any question, let's see if we could have no questions. We close the team.